Okay, so let's start. So the plan for today is to see two sets of results, at least start on two sets of things. So the first part, we are going to talk about local decoding of Reed-Muller codes. We defined the notion of local decoding yesterday. What's a locally decodable code? And we'll show that Reed-Muller codes, which are like a multivariate generalization of Reed-Solomon codes, are locally decodable with an interesting range of parameters. The second part, in the second part, we are going to show that Reed-Muller codes are also locally testable. So we'll define the notion of local testability. And we'll show that there is a local algorithm that given an arbitrary vector with the same parameters, distinguishes the cases where this vector is a Reed-Muller code word, or this is very far from every Reed-Muller code. So we'll talk about that in the second half. But for the first half, let's focus on local decoding. So does everybody recall the definition of local decoding? Not writing that. So we say that a code is locally decodable with parameters maybe t comma epsilon if there is necessarily a randomized algorithm that given access to a received word which is epsilon close to any code word, queries the received word at some t locations and outputs, and you are also given an index I as input and outputs the ith coordinate of the closest code word. So given that Reed-Muller codes are defined this way, the local decoding problem here, the input is going to be as follows. So our input is going to be a function This is a function from fq to the m to fq. Note that every code word in the Reed-Muller code is also a function from fq to the m to fq. And we are going to be given a location alpha, fq to the m. We will be promised that f is epsilon close to some code word in this code. So f is epsilon close to Rm, whatever parameters we have here. Okay, and our goal is to output. So let's say it's epsilon close to Rm k comma m. Let p be the closest code word. So p is the m-variate degree k polynomial whose encoding is closest to the function f. And our output has to be p of alpha. So we want to output the evaluation of p at the input alpha and want the algorithm to query f on at most t locations. Where t is something, note that the length of the vectors, the code words, is q to the n, and we should really think of t as something much smaller than the total length, the block length of the code. Is the setting clear? So we'll prove two versions of this theorem. In the first versions, we will show that so for k being at most q minus 2, Rm k comma m is q minus 1 comma 1 over let's say 100q locally decodable. So if epsilon is 1 over 100q, then we will be able to output p of alpha with high probability after querying the given function f at q minus 1 locations. So that's the first version of this theorem. This will have most of the ideas for how these algorithms go. And then we'll notice that we are being a little sloppy about it. If we use everything that we have seen so far, we'll actually be able to prove something more. So let's say if k is at most q over 2, then Rm k comma m is q minus 1 comma 1 over 100. So here we are tolerating 1 over 100 q fraction errors. And here we will tolerate 1 over 100 fraction errors, independent of q. The second parameter is epsilon. It's the fraction of error. So your received word, your input is epsilon far from a code word. What is that epsilon? So in the first version of this theorem, the epsilon is 1 over 100 q. And in the second version, epsilon is 1 over 100. Yeah. Note that the query complexity is roughly q for both of these algorithms. And q is much, much smaller than q to the m. Think of m as something large. So this is, it is an interesting regime of parameters. We aren't cheating. We aren't reading the whole thing, somehow decoding, doing a global decoding and then outputting the coordinate that you asked for. Questions about the statement? All right. Sorry. Yes. So so k is going to reduce, which means the dimension of the code reduces in a second. Yeah, q over 2 is liberal. We can. It's some constant fraction of q. To be important. Yes. No, the second is the distance. So we are saying there is a, the received word is epsilon. The distance between f, the Hamming distance between f and the code is at most epsilon n. And what is that epsilon? So in the first one, epsilon is 1 over 100 q. In the second one, epsilon is 1 over 100. Yeah. It's not. It's here, right? It's in the definition of the code. For Reed-Solomon, it's not interesting. The number of queries is q minus 1 here. For a Reed-Solomon code, the block length is q. So it's not really a local decoder. Other questions? Okay. So let's prove it. We'll start by proving this, and then we'll make some high-level observations on top of it. Notice that we know how we can actually get something better. Okay, so let's try to understand what the setup is. So we have f and we have p, and we are given the vector f. Okay, so these are all the evaluations and q to the n. P is the vector corresponding to p. And maybe we are interested in some coordinate alpha, which is here. Let's say this is alpha. So this is f of alpha, this is p of alpha. And we know that f and p are close together, but they disagree. They could potentially disagree at a few locations. And our goal is to find p of alpha given query access to f. And we want to do this while not reading all of f, in fact, querying f at a small number of locations. So for a minute, let's assume that we were given access to p. How do we get our hands on p of alpha? We can just go and read. Right? But suppose I'm given access to p and I messed this one entry up. So you understand what the setup is? So we are given the truth table of p, the evaluation table of p, and there is this entry p of alpha that I'm interested in. But that one entry I know is corrupted. I want to figure out p of alpha from the rest of p, and I want to do it somehow locally. What can we possibly do? What kind of a high-level structure would an algorithm have? Check what? Check. Good. Which k plus 1 entries? It's a multivariate, yeah. So, a local algorithm, even in this case, if I corrupt alpha and all the other entries are correct, a local algorithm in some sense has to behave in the following way, right? It has to figure out a few entries of p, few other entries of p, read the values here, and somehow infer this value from these values. Right? So we are talking about we are looking at evaluations of a multivariate polynomial at a bunch of points, and we are saying, well, the evaluation at this point depends on the evaluation at these 17 other points. That's the structure of the algorithm. That's almost by definition. So the question is, what are these local dependencies in the evaluations of a multivariate polynomial? If I give you a low degree polynomial, evaluate it everywhere in space, what kind of local dependencies do we see in the evaluations? And one kind of local dependencies that we see is something that Avantika was alluding to. So if we take so P is a degree K polynomial. It's an M-variate polynomial, so it is P of x1 up to xn. Now let's look at the restriction of P to a line. So let's say I'm going to look at the line LAB. This is a line in FQ to the M. What does that mean? This means these are points of the form A plus B times T, as T varies in FQ. Okay, and A and B are vectors in FQ to the M. So this is a line in FQ to the M. Now this line has Q points. So the size of LAB is Q. Now let's try to understand how P behaves on this line. Okay, what are the evaluations of P on this line? So let's look at so we are going to be looking at evaluations of P at points of the form this. Right? P of A plus BT, these are the points on the line. And if we write it carefully, this looks like P of A1 plus B1T, A2 plus B2T, and so on, AM plus BMT. And we vary T, we get these M tuples, and we are looking at the evaluations of P at these M tuples. But another way of looking at this is that let's look at the univariate polynomial Q of capital T. This is defined as P of A plus B times capital T. So capital T is a formal variable. And this just from definition is A1 plus B1 times capital T, A2 plus B2 times capital T, and so on, up to AM plus BM times capital T. So this is a univariate polynomial that we got by restricting the M-variate polynomial P to the line A plus BT. Is that clear? Great. What can we say about this univariate polynomial? What is its degree? How big can the degree of Q be? So degree of Q can be at most the degree of P. Right? It may be smaller. Sometimes it will be smaller on some lines, but it can never be larger than the degree of P. Okay, good. So which is K. So the degree of Q is at most K. The field is also Q, right? Let me call this something else. Let's call this R. So the degree of R is at most K. And now we want to look at, so looking at the evaluations of P on the points on this line is like looking at little q many evaluations of R. So LAB is Q points, which is strictly greater than K. So if we look at the values of P on points on this line, we are actually getting values of R on Q evaluations. So we have access to Q evaluations of R. So now we have a univariate polynomial of degree K, and we have Q of its evaluations, and we are in the setting that Q is greater than K. So we have a univariate polynomial of degree K, we have at least K plus 1 evaluations of this univariate polynomial. Right? So what happens in these cases? What do we do if we have a univariate polynomial with more evaluations than the degree? We can recover the polynomial exactly. Right? We know we can reconstruct the univariate polynomial R. So since Q is greater than the degree of R, we can reconstruct R uniquely from these evaluations. Is the setup clear? We had a multivariate polynomial. We wanted to understand what kind of local dependencies can be there between its evaluations in FQ to the n. One kind of local dependencies are we look at points on a line, we look at the evaluations of this polynomial on a line. That is a univariate polynomial of degree at most k. The size of the field is larger than k. So if we take any k plus 1 points on this line and look at the evaluations there, we can actually recover the polynomial itself, the univariate polynomial, and then we can evaluate it wherever we want on the line. Right? So that gives a kind of local dependency. Okay, good. So now given this, do you see a way of getting a local decoding algorithm, at least in this case, in the case that we have access to P, a table of P, except for this one location alpha, where we have where we don't have access. I want the value of P at alpha. So what should we do? Right. So the suggestion is we put A equals alpha. So we look at the line in the direction B through alpha for any vector B. So choose any direction B. Look at the line P of alpha plus BT. On that line, we don't have access to the evaluation at t equals 0. Right? We don't have access to P of alpha. But we have access to evaluations for all little t that is non-zero. So we have at least q minus 1 evaluations available to us. And hope I wrote this correctly. K is at most q minus 2. So we have access to q minus 1 evaluations of this univariate polynomial R. But the degree of R is at most q minus 2. So we can recover R exactly. And once we recover R exactly, we can evaluate it at t equals 0 and figure out what P of alpha is. Is that okay? So what is the algorithm? So the algorithm is, in this case, the algorithm is so find the unique degree k polynomial, univariate polynomial, R of t, such that for all t in FQ star, R of little t is equal to P of alpha plus B little t. So let's pick a B. So B is some non-zero vector in FQ to the m. So we pick an arbitrary B. We look at we find the unique degree k polynomial, unique degree k univariate R of t, such that for every little t in FQ star, R of little t is equal to P of alpha plus BT. Okay, this we can do by interpolation. The degree of R is strictly smaller than the number of evaluations we are given. So, and then output R of 0, which is equal to P of alpha plus B times 0, which is equal to P of alpha. Okay. Are we good? So if we were given access to the evaluations of P everywhere but on alpha, this is one way of reconstructing or recovering the evaluation at P of alpha. We never had to read P of alpha itself. We drew a line through alpha. We queried P on the line. Then we found the univariate polynomial, which is equal to the restriction of P on the line. And from that, we could figure this out. Great. Now, is everybody on board? Yeah. You want to fix m minus 1 arbitrary coordinates. Okay, and then do what? Good. You could do that. And in this case, even that will work. Yeah, but these are all leading questions. Eventually, I want to work with F and not P. And what you're saying, it's not immediately clear that it will work. Yeah, you have very small degrees of freedom available. Okay, good. So everybody on board so far? Great. So now we want to go from this baby case to the case that we don't have access to P, but we have access to F. And F and P are close together. They are not they're not the same, but they are close together. So what should we do? What's the natural thing to try and do? one potential thing to try and do is to run the exact same algorithm. We pick a b in fq to the m, which is non-zero. We run the exact same algorithm, except we don't have access to p. So we try and find an r such that r of little t is equal to f of alpha plus bt. Right, this is something that, this is a very natural thing. We don't have access to p, we have access to f, we know p and f are close together, we can just query f and try and do this. Right? What's the issue with that? The first issue with that is that the algorithm is deterministic. Right? This should have rung a bell. As of now, this is a deterministic algorithm. We convinced ourselves yesterday that we can't hope to get a locally decodable code where the algorithm is deterministic. So the problem is that if you fix an alpha, I am always querying the points on the same line. So maybe p and alpha, maybe p and f disagree on points on this specific line. The line whose direction is b is given by this algorithm. And then this will all not work out correctly. Right? Okay. So what should we do? Pick a random line. Right? This particular line was bad, but we could have run this algorithm for any line in space, any line through alpha. So let's pick a random line, and then we will argue that if you pick a random line, and because p and f are close together with reasonable probability, I mean the evaluations on the line will all be good, and then we are done. Is that okay? So let me just change this algorithm. So let's add a step 0. Pick a b in fq to the m, uniformly at random. This we can't query p anymore, but we will query f at alpha plus beta t, and we'll output r of 0. All right. That's the algorithm. The only thing that changed is that we are going to pick a b at random. We pick a random direction, look at the line through alpha in this random direction. We don't have access to p, so let's query f on these locations. Let's interpolate. Let's output r of 0. Okay. Question so far? All right. So let's, so the query complexity of the algorithm should be clear, right? I mean, we promised that this will be a q minus 1 query algorithm. This is clearly a q minus 1 query algorithm. We are only querying, we are only reading f, the q minus 1 values of f on this line. So it's a q minus 1 query algorithm. Let's argue that it's correct. Okay, so here's the first observation. And this is not difficult. This should be clear. The observation is that if p and f agree on all points on the line L of alpha b, maybe not on alpha. So if p and f agree everywhere on the line apart from the point alpha, then the algorithm is correct. Right? If p and f agree everywhere on the line apart from, I mean, all the points where we are querying, then this is the same algorithm as last time. So nothing changed. So the algorithm is correct. So this is an easy observation. I mean, the main claim that we'll prove is that if f and p agree on 1 minus 1 over 100 q fraction of points, so then probability over b that f and p agree on L alpha b minus alpha. This is at least 0.9. Okay. So note that this will complete the proof. It will complete the first part of the theorem. Are we good? Good. Okay. So yeah, why is this true? right? I mean, we're picking a random line through alpha, okay? The event we are looking at is the probability that none of the other points apart from alpha is a point where F and P disagree. Right? So, yeah, well, what's the easiest way of seeing this? So if you fix a point on this line, so we are picking a random line, fix a point on this line, then the probability that F and P disagree on this at this point is going to be equal to the probability that you're sampling a uniformly random point from space and F and P disagree. So that's about 1 over 100q. So the probability that there is an error for a fixed setting of little t in that algorithm is 1 over 100q. And we are querying roughly q points. So the expected number of erroneous points we are going to see, or rather, yeah, I mean, we can just do a union bound. The probability that there is an error at any of these points is about q times 1 over 100q, which is 1 over 100. Okay, so yeah, so let me just write the observation and leave it at that. So observation is that for so any fixed little t in fq star, probability over b that f of alpha plus bt is not equal to p of alpha plus bt. This is equal to 1 over 100. Okay. This is because we are sampling B uniformly at random, so you're covering the whole space. So this is one observation, and the second observation is that so now we are just doing a union bound over all the points that we are potentially querying. So the probability over B that there exists a T in FQ star such that f of alpha plus bt is not equal to p of alpha plus bt is yeah, I mean, it's at most q minus 1 times 1 over 100q, which is at most 1 over 100. Oh, you can't, I see. From where? From here? From here. Okay. Yeah. All right. So let me just write this part below. So this is at most q minus 1 times 1 over 100q, which is at most 1 over 100. So the probability over the choice of B that P and F will agree everywhere on the line apart from the point alpha is it's at least 0.99. And we have noticed that if F and P agree on all these points, then we'll get the value of P of alpha correctly. Is the algorithm clear? Very simple algorithm, yeah. Yeah. Good. No. Not as it is. And yeah, I mean, we also have to change the setting of parameters a little bit. Right now, we don't have enough points to be able to do that. If we don't have 2 evaluations, we can't figure this out. You have to reduce k, but it requires a little bit of care. Okay, other questions so far? Good. Okay, all right. So now so since this part is clear, now I want to say that we have been very sloppy in how we are analyzing this, considering everything we have seen so far. We can go from 1 to 2 almost immediately. What are we really doing? I mean, this whole algorithm is really trying to figure out a univariate polynomial from its evaluations. And in this analysis, we are in this setting where all the evaluations are correct. Right? But yesterday we saw that univariate polynomials are very robust to noise. And even if you give me evaluations of a univariate polynomial at a bunch of points where a fraction of them are incorrect, you can still figure out the univariate polynomial correctly. Right? Yeah. Okay. So if you notice between one of the differences between the two theorem statements is now we are asking for k being at most q over 2. So if k is at most q over 2, we are trying to interpolate a univariate polynomial from q minus 1 evaluations, right? So this is like looking at a Reed-Solomon code with block length being q minus 1 and degree being q over 2. So the distance of the code is about q over 2. And the Berkeley-Welch algorithm we saw yesterday can still recover the polynomial correctly if q over 4 of these locations is incorrect, right? We don't need all of them to be correct. Great. And this immediately lets us tolerate 1 over 100 error. I mean, we can increase the error tolerance from 1 over 100q to 1 over 100. Why? Because again, if P and F agree on 1 over 100, if P and F disagree on 1 over 100 fraction of locations, then the expected number of erroneous points you will see on this line that we have picked is going to be about q over 100. And q over 100 is much smaller than q over 4. So how does the algorithm change? The algorithm is again going to pick B from fq to the m at random. We are going to, so the second step will change now. We are going to look at these evaluations and we are going to use the Berkeley-Welch algorithm to find the unique degree k polynomial R which has large agreement with these evaluations. And then we'll output R of 0. Is that good? Okay. So, yeah, let me just mention here. So, we use Berkeley-Welch. What we are doing here is polynomial interpolation. What we should really be doing is noisy polynomial interpolation. It allows us to tolerate constant fraction errors. Is that good? Okay, I'm not going to analyze it, that's homework, but it's basically the same analysis. You just have to look at the expected number of errors and do some Markov and then you're good. Questions? No questions so far? Okay, so then let's move on to the second part of the lecture. We'll talk about local testing of Reed-Muller codes. And the main question here, so we haven't defined locally testable codes yet, but let me define it formally for this setting. So we want an algorithm. We want an algorithm that distinguishes if a given function, so again our input is going to be a function f from fq to the m to fq. If a given function is it's a Reed-Muller code, Reed-Muller code word, or it is far from all such code words. This is the testing part. We are given a function, we are given a received word f, and our goal is to figure out, is this a code word of the Reed-Muller code with parameters mk, let's say, or it's far from all such code words. And in general, this is the testing part of it. The local part of it is that we want to do this by not looking at the entire f. We want to do this by querying f at a small number of locations, and then from that somehow figuring this out. In general, a locally testable code, for a locally testable code, the question is similar. You are going to be given a received word and you want to distinguish if this is a valid code word or it's far from all such code words. And we would like to do this by querying the received dot at a few locations. Is the question clear? Okay, and again, we will have parameters of interest. We'll look at the query complexity. We'll have a parameter for how far it should be. So this is sort of a promise problem. We are given an input which is either closed, it's either a code word or it's far from all such code words. We have to figure out which one is which. Is the model clear? Okay. All right. So yeah, I mean, local testing is it's been an important ingredient for various things. So I don't want to go into that. But one of the reasons I find this problem interesting is because of how the algorithms look. So it's a natural question on its own, but I think it's even more interesting if you look at how clever some of these algorithms are and their analysis is. Great. Any suggestions on based on everything we have seen so far, what kind of a test should we do? What are natural ways of checking? So we are given a function, we want to check if this is really a low degree test, right? F being a code word just says that it's a low degree polynomial. It's a degree at most k polynomial on m variables. So we want to distinguish between the case that F is a low degree polynomial, it's the evaluation table of a low degree polynomial, or it's something that's far from all low degree polynomials. So it's what's called a low degree test. I mean, we have seen a few things so far. What's a natural thing to try? Remember, we want it to be local. So what should we try? Can you speak louder? Yeah, but we can't locally test read-Solomon codes. That's not very hard to prove. Right. What should we check on a line? Yeah, what? Right. So the suggestion is that, and we have been querying F on a line and doing local decoding. Let's pick a random line in space, query F on the line, and see if on the line this is a degree k univariate. If the values agree with it.
I guess what Sujata suggested is in spirit. I mean, we want to say, can you test if that thing is a univariate?
Is that what you meant? Oh, okay. Great. Then I misunderstood. Sorry. Yeah. So yeah, on the line, we are not doing anything local. We are doing global. Good. So that's a great suggestion. So so the suggestion is we will query F we'll pick a random line. I think you want to pick a random line. You don't. Yeah. So you want to pick a random line. You want to query F on the line, and you want to see if the values that we are reading are coming from a univariate polynomial of degree at most k. Clearly, if F is a code word, this test will always pass. And one has to argue that if F is far from all code words, then on a random line, this test should fail with reasonable probability. Right? That's something we will need to argue. Great. So the test we are going to see is not going to be the lines test. I mean, one of the things was to try and find a test which fits in a small amount of time. Yeah, I don't know too many low degree tests that fit in a small amount of time. In fact, the one we are going to do, I'm not entirely sure if it fits in a small amount of time. We'll see. So what we are going to do is we are going to do the same test, but on a plane. So we will sample a uniformly random plane in FQ to the M. We will query F on the plane and we will see, so on a plane, if F is a code word, what should it look like? What should the values on the plane look like? It should look like a low degree bivariate, right? It should be a bivariate polynomial of degree k on the plane. And if it is, then we accept. If it's not, then we reject. So, by the way, for the rest of this discussion, I'm going to focus on m equals 3. Okay, so for the rest of the discussion, m is equal to 3. And the test is, so pick a plane phi in FQ cube now, uniformly at random. If F restricted to pi is a degree k bivariate, then accept, else Yeah, because somehow planes are easier to analyze and it will fit in a yeah, 1 hour thing. Good. Great question. I think the plane test works in for all M. Swastik, is that right? Yeah, it works in all M. Yeah, the proof I'm going to do is for M equals 3. Yeah. Yes. Yeah, yeah. So I mean, yeah, it is true, but it takes some work to generalize it. Is that good? Is the test clear? What is the query complexity of this test? It's q square. I mean, the block length is q cube. We are querying it at q square locations. It's still significantly smaller than the block length, so it is a local test in that sense. All right, is the test clear? So the theorem we are going to see is a baby version of a theorem of Raz and Safra. And it says, so in this setting, it will say something like this. So if k is at most for all small enough constants epsilon and finite field fq, if a is at most epsilon q, and the test passes with probability 1 minus epsilon, then there is a degree k trivariate P, so P of XYZ, such that the agreement of F and P is at least, let's say, 1 minus 10 epsilon. So it's the contrapositive of what we would like to show. So we'll show that if K is sufficiently small compared to Q and the test passes with probability 1 minus epsilon, then F and P are actually pretty close. There is a low degree polynomial P, there's a degree K trivariate P such that F and P have agreement 1 minus 10 epsilon. This means that if the test, so then given this theorem, we can, what we can conclude is that if F is far from, if F is at least 1 minus 10 epsilon far from every low degree polynomial, then the test will accept with probability at most 1 minus epsilon. Okay. Questions about the theorem statement? I'll let you stare at it while I raise the board. Is the statement clear? So if we prove that, we are done. Okay. So the proof of this is going to be in a few steps. Okay, so So here's a definition that will be helpful. So the test is querying the polynomial at planes, at a random plane, and deciding whether to accept or reject based on whether the restriction is a low degree bivariate or not, a degree k bivariate or not. We'll say that two planes are consistent with each other. So planes pi and sigma are consistent if a little bit of notation that will help us write things clearly. So for any plane pi, I will use g sub pi to be the bivariate degree k polynomial, which equals equal to f restricted to pi. Assuming that pi is a plane on which the test passed, it means f restricted to pi is a degree k bivariate polynomial. G sub pi will denote that polynomial. So see, easy to define in this setting. So if planes pi and sigma are said to be consistent, if G sub pi and G sub sigma, they agree on the points where the planes intersect. So they agree on pi intersect sigma. These are two planes. If they intersect, then they are giving you values at common points. They better agree on these common points. And if pi and sigma don't intersect, then this is vacuously true. Is that okay? All right. What if G doesn't exist? No, yeah, I mean, this definition is only for planes on which G will exist. Yeah. Okay. Otherwise, we say they are inconsistent. A plane on which test doesn't pass is inconsistent with everyone. Great. So given this definition, what can we say about the consistency of two random planes? If I pick, we know that the test passes with probability 1 minus epsilon. So on 1 minus epsilon fraction of all planes, the restriction of f is a degree k bivariate. Now suppose we pick pi and sigma at random. What's the probability that pi and sigma are consistent? Right. Right. So if the test passed on both pi and sigma, then they must be consistent. Right? Because if the test passed on both pi and sigma, then the values of the polynomial of the function f on pi is a degree k bivariate with value being equal to the value of f. Similarly on sigma, so they at the common points, their values equals the values of f at those points. So what's the probability that pi and sigma are consistent? It's at least 1 minus epsilon squared, or something like 1 minus 2 epsilon. So probability over pi and sigma that pi and sigma are consistent is at least 1 minus yeah. The test was that the restriction on the plane pi must be a low degree polynomial. So G pi agrees with f everywhere on the plane. G sigma agrees with f everywhere on sigma, so they will agree on the common. Okay, are we good? Okay, great. So now the plan is the following. So we'll show two things. We'll show that so there is a large collection of planes that are all consistent with each other. So we'll show that there's a large collection. How large? Pretty large. So I mean something like 1 minus yeah, I don't know. 10 epsilon, it will this set will contain something like 1 minus 2 10 epsilon fraction of all planes. So there's a large collection of planes, there's a large set of planes that are all consistent with each other. This would be the first part of the argument. The second part would be that there is a degree k trivariate P such that for all pi in the, let's say, set, let's call this set U. So for all pi in U, G sub pi equals P sub pi. So in the first step, we'll show that there's a large subset of planes that are all consistent with each other. And then we'll show that there is a degree k trivariate such that on all of these planes, the function G sub pi equals the restriction of P on pi. Are we good so far? Okay. Given these two steps, I want to claim that we will get the conclusion easily. So we want to say that this degree k trivariate P that we have somehow gotten our hands on actually agrees with F at a large number of locations. Why is that true? Right. I mean, P clearly agrees with F everywhere on every point in the union of these planes. And since this collection is really large, the union of these planes will be practically everything. So from here to that theorem is an easy argument. Okay? Yeah, I mean, you need to think about it for a minute, but it should be believable that we have a large collection of planes and we have a low degree polynomial that agrees with, that's consistent with F on all these planes. So this must cover a large fraction of all points in space. Right. That statement, yeah, that's a combinatorial statement. So the easy observation is that P agrees with F on maybe 1 minus 10 epsilon fraction of all points. Oh, by the way, these 10s may be different. This may be a larger 10 than this 10, so maybe 100. Let's make it 100 all points. Okay, questions so far? So that's the plan. We have 5 minutes, Prahladh. We have more than 5 minutes? We have 7 minutes, okay. All right, are we good? So let's at least do the first part of it today, and then we'll do the second part tomorrow. Yeah. Do people see how to do the first part? Right? Right? Right, but you have to get a large collection and you want all pairs to be consistent. Right? You want a large subset such that every pair of planes in this subset are consistent with each other. So here's one way of doing this. We can plot this information in a graph. So let's plot it in a graph. So we have G, V, E. V is the set of all planes. In FQ cube. And E is the set of planes pi sigma such that pi and sigma are consistent. Okay. Then what is this a statement about in this graph? It's a statement about this graph having a large clique. what do we know about this graph? How many vertices does it have, by the way? Roughly how many vertices? What is the size of V? How many planes are there in FQQ? No, what is the total number of planes? It's around QQ. That's the scale of things we are talking about. All right, and we know that if we pick pi and sigma at random, then they are consistent with probability 1 minus 10 epsilon. So this graph is really dense. It's so if you pick pi and sigma at random, then they are going to be, 1 minus 10 epsilon fraction of such pairs are going to have an edge. Right? So probability over pi sigma in V. Pi sigma is an edge. This is the same as probability that pi and sigma are consistent. And this we have argued, this is roughly a 1 minus 10 epsilon. So this graph on average has a very high degree. Most of the edges that could have been there are there. Okay, so I claim that this graph has a large clique. Thuran's theorem. What would be the size of the clique? So we are going to lose. Is that enough? Is that going to be enough? No, right? Yeah, we need a clique of super large size. We need a clique of size nearly everything. So, all right. So I'll make two observations. Observation one is that if for a pair pi and sigma, if pi sigma are not consistent with each other, then at least one of pi or sigma must be inconsistent with at least something like 1 minus k over q minus k of 1 fraction of all planes. So Srijato, this is not a combinatorial statement. It does use algebra. Okay, so we want to conclude that there is a large clique in the graph. The observation is that if you take two vertices that aren't adjacent to each other, then one of them must actually not be adjacent with a lot of other vertices, nearly half of all the vertices in the graph. Okay. Observation 2. So observation 1 implies that if you look at the set of all vertices with large degree larger than so the degree of these vertices will be at most half times 1 plus k over q. Right? If something is inconsistent with half minus k over q. So the set of, so let's define U to be the set of all pi such that the degree of pi is greater than half 1 plus k over q. Okay. Then U forms a clique. So we take all vertices of somewhat large degree and they will form a clique. Why would they form a clique? Well, that should be clear from this. If any two of them are, if you have an inconsistent pair, then at least one of them has a large degree. One of them has a small degree, and every vertex in the set U has a large degree. And I hope, yeah, this matches. Is that okay? Great. So going from here to here, by the way, now that we know that all vertices with large degree form a clique, we would like to conclude that there is a large clique by showing that most of the vertices in this graph actually have large degree, have degree larger than half 1 plus k over q. So observation 3 is that the size of U is large times the size of. Going from observation 2 to observation 3 is just a combinatorial consequence of the fact that the average degree in this graph is very high. This is a very dense graph. So there can't be too many vertices whose degree is this small. So most vertices have large degree. So 2 to 3 is it's just a consequence of the fact that the graph is dense. Observation 1 really shouldn't be an observation. Maybe it should be a let's make it a lemma. Prahladh, we are out of time. Okay. I'll not rush through it. I'll do it next time. Okay, is the plan clear so far? The only thing that we haven't proved is lemma 1. If we prove lemma 1, we get that, this lemma will immediately imply this observation that if we look at the set of vertices with large degree in this graph, they must form a clique. And this graph is we have already established that the average degree in this graph is quite high. From that, we will conclude that the set of vertices with degree larger than half 1 plus epsilon 1 plus k over q should be practically everything. So the only thing we haven't proven here is this. Once we prove this lemma, this will conclude our step 1. And then we'll go and do other things to prove step 2. Okay, so let's stop here and we'll start from here next time and continue.